Till now we have learned the Euler methods. That is the first order Longa-Coulomb method, and the Heon method or the improved Euler methods. That is the second Longa-Coulomb methods, and the fourth Longa-Coulomb methods. We can use those methods and the formulas to solve the ODE IVPs. But here we are going to use the MATLAB's solvers. Here are the two major solvers. One is Bbe2003. This for solving the non-stiff ODEs. This is another function, ODE2003. This is for solving the stiff ODEs. These are the format, how to call these two functions. Very similar. The first input is the function. Okay, the function handle. And this is the interval of the independent variable. And this is the initial value. And this is the options. These are the additional parameters. Look at this ODE IVPs example. ODE function and initial condition. To solve this ODE IVP, we need to write a function definition first. This is the definition of the ODE function, right? So you define the right hand side expression. This is the right hand side function here. Okay. And dy actually represents the value of the first derivative. After definition of the ODE function, then we can call Bbe2003, right? Add function name here. Okay. Expand here is the interval of x. X is from 0 to 10. 2 is the initial value given here at x equals 0, y equals 2. So this measure, then we can calculate x, y. Y is the value at x. These are two vectors, right? In previous slide, we only learned about the first order ODEs. So, how to solve the higher order ODEs? The first step is to reduce the high order ODE to first order ODEs. Then we can use the same ODE functions, ODE solver to solve them. For the high order ODE like this is the high order ODE and the corresponding initial condition given. So we need to set y1 equal y, y2 equal y prime, y3 equal y prime prime, etc. Then the higher order ODE can becomes the first order ODE like this. Right? Because from this y1 equal y, we take first order on both sides, then we get y1 prime equal y prime, right? The y prime here actually y2. So y1 prime equal y2. Right? So similarly we get y2 prime equal y3. y3 prime equal y4, etc. Accordingly, we need to convert the initial condition y, because y equal y1, right, here. So now become y1a equal y10. y10 actually here is y0. Okay. And we derive the other is, then we can use the ODE function, ODE45 or ODE2003s to solve these ODE equations. Here is the example of the higher order ODEs. Look at this. This is the second order ODE. We usually need to convert this to the first order first, given the initial condition. They are second order, so usually there are two initial conditions given. For the third order ODEs, there will be three conditions. Okay. So how to convert it to the first order ODEs? We need to set y1 equal y and y2 equal y prime. Then the second order become two equations of first order ODE. Right? Say here y1 equal y2. So taking the first order derivative on both sides of this, there will be y1 prime equal y prime, right? Because y prime equal y2 here. So y1 prime equal y2. Then y prime actually, yeah, you can convert here, right? Y prime equal y2, plug into y, actually y1, right? And then you get this second ODE. Accordingly, you convert the initial condition here, because y the same as y equal y1, so you get y1 0 equal 1, right? y2 equal 0. Here y prime equal y2, so that is y2 equal 2. Okay, then next you simply use the same ODE equation to solve this. Here is an engineering example about the anaerobic batch fermentation of glucose. Fermentation of glucose with a kind of yeast to produce ethanol and byproduct carbon dioxide. The feedstock used to contain 4% glucose. This initial concentration of the feedstock, and the inoculum is this concentration of inoculum. The cells stop growing at the concentration of 14% ethanol due to the product inhibition. Please simulate the change of concentration of a component from time 0 to 15 hours. Given the initial condition here, this is actually summarized from here. X0, S0 is the glucose concentration, initial glucose concentration. P0, the product, 0, etc. So for this engineering program, you simply browse this description, but if you don't understand, that's fine, because currently you haven't learned about this. Okay, you can even skip it, but I suggest you quickly read this, okay, whether you understand or not. But usually I will give the summarize the initial condition right here. So you simply look at the symbols, okay, and I also give the specific model below. So just like here, the parameters are summarized here. Okay. Initial condition, you simply focus on initial condition and the parameters. And next, also the ODE equations. Here is the code for the batch fermentation. You see here, first step, you simply list all the given parameter, right? Parameter, leave all the known parameter, known data, and then specify the initial conditions. Okay. And then you define the ODE functions in the next line. Okay. And then you call ODE45 to calculate, right? You specify the time span, x from the time from 0 to 15. And these are the initial concentration at time 0. Okay. These are all the parameters in the models. So here is the remaining code of the program. So the model function defined here, right? We have three. This is a kinetic function. Three ODE equations. And after calculation, you simply plot the curve. So here is the result, right? The ethanol is this curve. The product ethanol increase with time, right? The glucose is the phi, right? The glucose concentration decrease over time. The product increase over time. And this the live cells also increase with time. This is another example. Biomass pyrolysis for production of biofuel. A waste biomass is used for producing biogas and bio-oil by pyrolysis under this temperature, high temperature. The reaction mechanism is shown below. This is the reaction mechanism. The feedstock, right? Biomass. There are several reactions. Converted to C, right? Converted to B. B is the oil plus water, we call B. Product C is the carbon 1 to 4. Okay. We use the lump parameter, lump components. Then the equation for IVPs, we get the ODE equation, right? Ca, Cb, Cs are concentration of IVPs respectively, and K1, K2 are reaction constants here at time 0, Ca given, Cb given, Cc given. So this is initial condition. Simulate the pyrolysis process. So that means solving this equation. The method of code is similar to the exam 2. Here the result. You can see here, right? Oak. In this case, oak is the biomass, the feedstock. So the biomass concentration decrease with time, right? Because it's converted to the product. Oil increase with time first and reach a peak, then decrease with time. In summary, the Euler methods and Hiller method are the simplest arcade methods for solving ODE IVPs. They are less used because low accuracy. Step size must be small enough to maintain the numerical stability. We usually use the fourth order longitudinal methods, the fourth order. And of course, it is suggested we use the built-in function